All right, next organ is the adrenal gland. So we're going to talk about the different parts and regions of the adrenal gland because they will do different things, and so we got to talk about each region and their contribution. We'll talk about the role of aldosterone and its secretion and what the pathways it's part of. We'll talk about glucocorticoids and their role, and then get into the adrenal medulla when it comes to response to stress and what hormones are released there, and then get into some of the fight or flight type things like the epinephrine and norepinephrine, or what we would better know as adrenaline. We'll also talk about the adrenal cortex and medulla and how they help respond to stress over short term and long term. And then we'll talk about a couple different disorders when there is an issue with the adrenal gland. So there are two adrenal glands, right? There's going to be one sitting on top of each kidney, so you have two kidneys, which means two adrenal glands. I like to say like they're like the little party hats of the kidneys, if that helps you remember. But the adrenal glands are sitting right above those kidneys, and they have two main regions: the cortex and the medulla. Cortex, and hopefully you remember this from anatomy. If not, I'm here to remind you. Things that are called a cortex tend to be an outer layer or an outer aspect, whereas a medulla tends to be the middle, right, or the inner part. So think medulla is middle, and then cortex is almost like a capsule around it. So the cortex, right, has three different layers: the zona glomerulosa. It's going to be outer layer, the zona fasciculata in the middle, and then the zona reticularis, which is in the innermost layer of the cortex. And the medulla is just on its own. So if we look at where we see this, right, just to kind of remind yourself of the anatomy, right, we have the zona glomerulosa, we have the fasciculata, and then reticularis, seen in those three colors, and then the medulla is all this seen here in the middle. So let's talk about the cortex and what it does first. We have three different categories of hormones coming from the adrenal cortex. They all have the same base, which is cholesterol. And again, they're all made in different regions, right, in those different layers. We have the mineralocorticoids, the glucocorticoids, and the adrenal androgens. So mineralocorticoids will regulate minerals like salts, so sodium, potassium ions, right? This will help regulate that in the blood. It's going to impact the kidney, right? If the kidney is going to kind of reabsorb them or not. It also goes along with water. And it's going to help basically control your water and blood volume. This is coming from the zona glomerulosa. You can remember this because the glomerulus is part of that kidney. So mineralocorticoids like aldosterone impact the zona glomerulosa. They're impacting the kidneys. Glucocorticoids regulate glucose metabolism, so like cortisol. This is coming from the zona fasciculata. I don't have a trick for that one. And then lastly, the adrenal androgens like DHEA are going to supplement what's made in the gonads. This is coming from the zona reticularis. So let's talk about aldosterone because this is a big one. This is the major mineralocorticoid. This is going to regulate your salt and water balance, so things like your sodium ions and your potassium ions along with water. The secretion of aldosterone is going to be controlled by renin-angiotensin-aldosterone, or RAA pathway. So these are going to be the three hormones that are involved in this pathway. Right, so basically what happens is the kidney, right, this pathway in the kidney is stimulated by blood pressure changing or blood volume changing, namely if blood pressure or blood volume drop. And so if blood pressure or blood volume drop, we need to increase the volume or increase the pressure, and that means we need to increase the reabsorption of water and sodium ions, right? Because the water will give us volume. The sodium helps draw that water in as well. And so that will increase the volume, it'll increase the pressure. So if we kind of like watch this right in place, so blood pressure has dropped. Oh no. Right, we detect that in the kidneys, we are going to release renin, which is then going to send us down this pathway of angiotensinogen. Oh man, angiotensinogen tells us we're inactive, but renin activates us, right, to angiotensin 1, then to angiotensin 2, which that will then stimulate the production and the release of aldosterone. Aldosterone will tell the kidneys and help the kidneys reabsorb water, reabsorb sodium. Sodium retention happens, water goes along with it, blood pressure goes back up. Right? So we're not going to talk about what angiotensin 2 does over here. We're just going to kind of focus on this pathway, right, that I traced with my mouse. But that's the pathway we're seeing, right? So the renin, angiotensin, aldosterone pathway is the three hormones, right, or three groups of hormones, I should say, that are going to help increase blood volume or blood pressure, right? And we're increasing blood volume and blood pressure because we are increasing how much sodium we retain. So we're going to keep more sodium instead of excreting it out. And when we keep more sodium, that's going to draw water along with it, right, through osmosis. So take a peek. Again, just a different view of the same thing, but where blood pressure has dropped, our fluid volume has dropped, renin gets released by the kidney, right? That is going to activate our angiotensinogen to angiotensin, right? So it acts on that. We now are angiotensin. Remember, anything with ogen is going to be an enzyme that is not in its activated form. We then have ACE, right? Angiotensin converting enzyme. That's what the ACE stands for, from the lungs, which then goes from angiotensin to angio 1 to 2. And then from there, right, we stimulate the adrenal glands to release aldosterone. Aldosterone then tells the kidneys, hey, pull up more salt and pull up more water, right? Angiotensin also goes right to the blood vessels, which is going to basically cause vasoconstriction, so it's going to tighten down, which increases blood pressure, and this is why you see some medications like ACE inhibitors that will be used to lower blood pressure, right? ACE inhibitors inhibits this enzyme, which means we don't form angiotensin 2, which means we don't see that vasoconstriction. Moving on to glucocorticoids. This is a big group, but it includes things like cortisol, cortisone, and corticosterone. This is going to stimulate osteoclast activity, so thinning of the bones, osteoporosis are going to be related to this if you have too much of this. It will stimulate protein and lipolysis breakdown, glycogenolysis or glycogenolysis, right, and gluconeogenesis in the liver, so we're going to increase blood glucose with these. It is going to give us physiological resistance to stress. It has, it's going to increase vascular tone. It's going to increase blood pressure. It's going to help reduce pain, and it's going to have an anti-inflammatory effect, right? So you need these to some degree. So there are some synthetics like hydrocortisone, dexamethasone. This is to suppress inflammation. Because if you naturally, if you're naturally producing your glucocorticoids, it's anti-inflammatory. If you have a condition like Addison's, this can kind of do the job of the hormones you don't produce. So like Addison's, you're not producing enough of these, and so inflammation can have like a runaway effect. Synthetics can help control that to suppress that inflammation, but like any treatment, the natural way is usually going to have fewer problems, like having your natural level of glucocorticoids at a higher, at their normal level is going to be more beneficial than taking a medication. However, for some people, right, they don't have a choice because they have some sort of condition, like an autoimmune condition or something like Addison's disease, and so they would have to take this and find the right dosage that will give them the ability to manage their disease without having too many negative side effects. So glucocorticoids are controlled by a negative feedback loop, right? So our CRH is released, right? The secretion stimulated by CRH from the hypothalamus. This tells the anterior pituitary to release ACTH. ACTH then tells us to produce and secrete things like cortisol. That will then, once you have a high enough amount of cortisol, we can act on the anterior pituitary and hypothalamus, just like we've seen before, right? That negative feedback loop, we have enough cortisol, so stop the production. But stress can also have that impact, right? So we have those metabolic effects. Stress will then positively increase or positively affect the release of these hormones, increasing cortisol. If we look at the major androgens, the main one is DHEA. So DHEA, we don't really see this having much of an impact in males because they have testosterone, and that's just in much higher amounts. But in females, right, this as well as other androgens will play a role in promoting things like libido and also convert to estrogens. When we go through something like menopause, those estrogens come from the adrenal androgens, right? So we're making that conversion. I'm not as worried about this one though. So when it comes to the adrenal gland, I'd rather you focus on the mineral corticoids and the glucocorticoids. Now let's move to the medulla, the middle. This is going to be directly connected to the nervous system, right? So this is going to be stimulated by the sympathetic preganglionic neurons. Those preganglionic neurons make their way from the spinal cord all the way to the adrenal. And this is going to be part of your sympathetic side of your autonomic nervous system. Basically, it's part of your fight or flight response, right? You have chromaffin cells, which are from this, they're going to be neuroendocrine tissues, so they're going to be kind of related to, they're going to be that in between. They're going to secrete epinephrine, which you know as adrenaline maybe, and norepinephrine or noradrenaline for your fight or flight or sometimes better known as a fight, flight, or freeze response. Basically, it's your short-term stress or your immediate stress response. So something happens, right, that you need to do something at that moment for immediate survival. So the fight, right, flight, I need to run, or freeze, I need to just stay still. Those are all actions that can be promoted by that. But generally speaking, there is the same type of physiological effects, which would be like things like increased blood glucose levels, preparing the muscles for movement, right, for immediate movement, increase in respiration, increase in heart rate. The mouth would get very dry, right? Digestion would slow. Those are all going to happen regardless if you fight, flight, or freeze, right? That's just the generic stress response there. But it's a survival adaptation because we're trying to manage a dangerous short-term situation. If we have this going on, if we have this release long-term, this can be very damaging. So what do epinephrine and norepinephrine do? They are catecholamines, so they're basically derived from amino acids. Again, the sympathetic nervous system directly innervates the adrenal medulla, and the effects that we're going to get are things like increased cardio output, so our heart rate, right, and all that's going to increase. We're going to breathe heavier, breathe deeper, we're going to be more alert. Our metabolic rates are going to increase, in that we're going to be prepared, right, to use up resources very quickly. Things like digestion, things that are going to be like that are going to be downplayed since we don't necessarily need that function occurring in that moment, right? We're just really worried about immediate survival. So we look at stress response, long-term versus short-term. So stress response is coordinated by these two parts of the adrenal, the medulla and the cortex, when they're stimulated by the hypothalamus. So we have the hypothalamus that helps us perceive that stress, and that can trigger the sympathetic division, so releasing like epinephrine, releasing norepinephrine to increase cardiopulmonary response and suppress non-emergency processes. So basically, we're preparing our heart, our lungs, and our muscles and whatnot to immediately respond. Everything else, like digestion, right, that kind of stuff, we are going to suppress, right? So we do that first. The sympathetic innervation of the adrenal medulla then allows us to release these hormones. This is going to amplify, right, the cardiopulmonary and vascular response and suppress all the other things we don't need. And then once that short-term situation is over, we need to return to normal. This is where the parasympathetic division of the nervous system comes in. And so we then go back down to normal, right? But long-term, right, hypothalamus perceives stress. We trigger the anterior pituitary to release ACTH. That tells the adrenal cortex to release cortisol, right? This is going to support the same body systems by mobilizing energy and suppressing the non-emergency things, right? Cortisol will have negative feedback loop though. So once we have enough of that, right, then we will slow down the production, right, produced by the hypothalamus. So let's take a look what's going on. So on the short-term end, right, short-term stress, immediate things, right, what's going to happen? We have a nerve impulse that goes to the spinal cord. Our preganglionic sympathetic nerve from the spinal cord is going to travel directly to the adrenal medulla. That's going to that's going to trigger the adrenal medulla to release things like epinephrine, norepinephrine. And so what happens immediately is heart rate goes up, blood pressure goes up, bronchioles in the lungs dilate, so we're breathing, in more oxygen basically. We're going to break down glycogen to glucose and release, and so our blood glucose level goes up. We're going to reduce the digestive system's functions. We're going to reduce urine output, and our metabolic rate will increase overall. But let's say we're given prolonged stress. Here we're going to focus on the adrenal cortex. So hypothalamus releases CRH, so the corticotropin releasing hormone. That's going to tell the anterior pituitary to release ACTH. Adrenal cortex then secretes mineralocorticoids and glucocorticoids, which will then tell the kidneys to retain sodium and water. It will increase our blood volume and blood pressure. It will convert proteins and fats to glucose for energy. Blood glucose goes up, and the immune system is also slightly suppressed. So you can see why long-term, being exposed to stress in a long period of time, like more than normal, can be problematic, because you're going to have an increase in blood pressure, you're going to have an increase in blood glucose levels, and you're going to have a suppressed immune system, which then puts you at risk. So, some of these things you do need to do on a regular basis. So long-term stress responses in general are not always bad, but if you are always exposed to high levels of long-term stress and you're seeing these things happen all the time, then that becomes problematic. So what goes wrong? Let's talk about Cushing's syndrome first. This is where glucocorticoids are too high. So lipolysis is going to occur, and there's a redistribution of fat. Basically, we see it develop more around the belly, the face, the shoulders. So the limbs, the arms and legs would get very thin in comparison to the rest of the body, which would then have what we call a moon-like face, where that person's face would seem very puffy and very round compared to what it was like beforehand. And the fat distribution would seem abnormal, right? In that it would be very much kind of connected to the core, including between the shoulders, behind the back of the neck. So there's almost like a little bit of a bump that develops there. And the limbs would be very thin in comparison. This can be because of a pituitary tumor, right? Or like some sort of benign tumor that basically, in the pituitary gland, that the pituitary is overproducing ACTH. It could be a tumor in the adrenals that basically we're making and releasing cortisol without the ACTH being high. It can also be because of synthetic hormones that we give, so medications. So things like prednisone, right? That would be an example of a long-term steroid someone may be given, or that would be problematic. So you see someone who has to take those types of medications, they get a very similar appearance because of that high level. Now, they may need that for other reasons, like some sort of inflammatory disease, and so it's something that needs to be monitored, and it's something that needs to be controlled by a doctor, right? A doctor needs to come in and be like, hey, we need to find the right dose for you that's going to both treat the inflammatory disease, but also not have so many negative side effects that the person's life is negatively impacted on another level. Addison's is where we don't produce enough, so there's an underproduction. If we have too little cortisol, we end up with hypoglycemia, so our blood glucose is low. We don't produce enough aldosterone, so we end up with salt imbalances or electrolyte imbalances. Dehydration can occur because we are not retaining that water, and blood pressure can be very, very low. Most of the time, this is from an autoimmune condition where the immune system is destroying parts of the adrenal cortex, or someone has an infection that has gotten to the adrenal cortex. This can be fatal if a person is not treated with a cortisol replacement, if they are just not producing enough. So Cushing's and Addison's are basically, in a way, opposites of each other, kind of, sort of, right? They're kind of almost opposite of each other.